Hello everyone, today we'll talk about chapter 4, Earth, Moon, and the Sky. It is the motion of the Earth that actually produces season and gives us the measures of time and the date. And the Moon's motion around us provides the concept of the months and the cycle of lunar phase. So in this chapter, we'll examine some of these basic phenomena and get a better understanding of those phenomena. First, let's look at the Earth and the sky. And let's look at how we actually locate a specific location on the Earth. You may have heard about that before. And it may be easier to locate a location in a city because we have different buildings, the road as a reference. However, imagine you are sailing a ship and on the sea there's no road, no references. So therefore, the terrestrial coordinate system is very, very useful. There is actually two coordinates for this system. One is a latitude and the other is longitude. Latitude, you can imagine, we actually start from the equator. The equator is a 0 latitude, and if you go all the way to the north, you will have increased number of degrees. And if we go all the way to the North Pole, there's a 19 degree north of the latitude. And the similar idea apply if you go from equator to the southern hemisphere. The South Pole, which is 19 degrees south of the latitude. And the longitude are a series of semicircles that's connecting North Pole and the South Pole. And the longitude, the 0 longitude actually located at the Royal Observatory and Greenwich. And you can see because the longitude actually denotes direction of east or west. So therefore, if we start from longitude 0, if we go to west, you will have a certain degree at the west. And on the other direction, if we go east, then we'll have a certain degree at the east. Similar to the coordinate system on the Earth, the sky also have a coordinate system. I hope you still remember that the celestial sphere we talked about in previous chapters. So this coordinate system we call it celestial coordinate system, similar as latitude and longitude. We also have two coordinates to specifically describe a location of a star on the celestial coordinates. The first one we call declination, which is very similar as the latitude on the Earth. So the declination 0 degree is at celestial equator. Remember, that is a line extend from Earth's equator and intersect with celestial sphere. And similarly, if you go all the way to north, you actually increase the degree, the number here, all the way to 19 degree north to the North Celestial Pole. And in the south, you have a similar thing, and South Celestial Pole give you 19 degree declination, but it is south. And the right ascension is similar as longitude. Right ascension is basically those semicircular lines connect between the North Celestial Pole and the South Celestial Pole. However, there is not really a star we assign 0, the starting point of the right ascension. Instead, we set the 0 right ascension at the vernal equinox. It's basically right here. And usually the right ascension we assign the units with hour. So for example, that is a 0 hour. It is because we take into account of Earth's rotation. To appear to us, the stars or the night sky is rotated around the Earth throughout a day. Right ascension and declination are very useful coordinate system which can help us to locate a star. For example, if you want to do an observation of a certain star, there are so many stars look like each other. So how you know exactly which star you are looking at? As long as you can give the exact coordinates, the number for declination and the number for right ascension, we will locate the specific star you are mentioned to. Next, we're going to talk about another very basic phenomenon, which is the season. So, from your everyday experience, you definitely know that in summer it's hotter and in winter it's colder. That is actually a common misunderstanding or misconception that the reason we have summer because Earth is closer to the sun, and during the winter, the Earth is actually further away from the sun. This is actually not the truth. And when we measure the average distance from the Earth to the Sun, we actually found that the Earth is actually closest to the Sun in January. And if you remember, we talked about the Earth's orbit around the Sun. Earth's orbit is only a few degrees off from a perfect circle, so it's not like such a significant differences between summer and winter in terms of Earth's distance from the Sun. And a couple other reasons you can imagine that the tropical area are warm all year round. It doesn't matter summer or the winter. And when we enjoy the summer in the northern hemisphere, the southern hemisphere is actually in winter. While the northern hemisphere is in winter, the southern hemisphere is in summer. So this season is actually not due to the different distance Earth away from the sun. Instead, it actually have something to do with how the sunlight angle shine on the surface of the Earth. Because you can see Earth's rotational axis is not exactly perpendicular to Earth's orbits around the sun. So this is 23.5 degree tilt of Earth's axis of rotation is actually the cause of the season. Then how this angle actually make us feel differently in summer and winter. First, let's go ahead to look at Earth's orbit around the Sun. You can see at different time of the year, the Earth actually at different location on its orbit to the Sun. Let's first look at the summer. So, you can see in this picture, when it is the summer, basically that is the time the Earth northern hemisphere is actually can see is tilted towards the sun. Therefore, you can see the sunlight is more straight down to the northern hemisphere. And the amount of heat the surface actually receives is actually depends on the angle. You can see in terms, for example, there are 5 light rays, and for each area of the ground, one, the sunlight's angle is at large angle. Then that means for each certain area on the surface, you are able to receive more sunlight. So therefore, that is one of the reason the summer is hot. And the other reason you may remember that the day for the summer is actually longer. That is the second reason, because it's gonna be there are more time the Earth's surface actually receive heat from the sunlight. So basically, that is basically the sun was in the sky for a longer amount of time. These two reasons add together and result to the more heat actually absorbed by the ground from the sun, and which result hot summer. And on the opposite side, when the Earth's or the northern hemisphere is in winter time. You can see during the winter, the sunlight actually has more streaks shining on the southern hemisphere. So therefore, if you look at the northern hemisphere, that the angle of the sunlight is pretty small. So therefore, the certain area is actually will receive less amount of heat from sunlight. And that is one reason. And the other reason is that you may not also remember that the day during the winter in northern hemisphere is actually very short. Therefore, there is a less amount of time we can receive the heat from the sunlight. So as a result, we actually have a colder winter. While we are in the winter, we are experience the cold weather. You can see the southern hemisphere actually is exactly what happens when the northern hemisphere is in the summer. So the sun actually have a large angle on southern hemisphere. So that is why the season is actually flipped. So this is summer and winter. And there's also two other locations on the Earth's orbit we call vernal equinox, which you can see is about March 21st. Sometimes we call it the first day of spring, or the autumnal equinox, which is September 21st. We call the first day of fall. On those 2 days, we actually, it's not as hot in the summer, not as cold as in the winter. So you can see that the sun exactly spent like half day, about 12 hours above the sky. So it's not too long, the day is not too long, the day is not too short. Now let's look at the simulation. So we'll place all the way to the start of the year, and we'll place the people to an average like latitude of North America of US. You can see start from January, the sunlight gradually increase the angle. So therefore, we're actually in the process of warm up. So you can see gradually the angle become larger and larger. The angle keep increase until June 21st, which the summer solstice. And after that, you can see the angle start from become smaller and smaller. So we'll basically receive less amount of heat from the sunlight. And all the way, you can see to the December will become colder. You may be wondering, the day we actually receive most of the heat from the sun and have the longest day is June 21st, but it's not the hottest month on the Earth. It's because the surface actually absorbs the heat from the sun, and it will take some time for the Earth's surface to radiate this heat back into the air. So therefore, there is some logging of you feel the heat actually be trapped in the air. So therefore, the hottest month for the northern hemisphere is not happening in June, but it's a little bit later, like July and August. On top of that, there's also a lot of other factors contribute to the heat, as well as like if it's on the seaside or in the mountain. So that is a little bit complicated. But if you talk about the season, the cycle of the season is actually result from this 23.5 degree tilt of the Earth's axis of rotation. Next, let's look at a phenomenon also very easy to observe from the Earth, which is the phase of the moon. So you probably heard about the full moon, and like the crescent moon, the quarter moon, the gibbous moon. So in this class, we'll talk about a little bit detail why on the Earth we're able to observe different phase of the moon, and what is the relative location of the sun, the moon, and the Earth give us the different phase of the moon. If you look at the moon is always, the half of the moon is actually lighted up by the sunlight. However, the reason why we see different phases of the moon is because from the perspective of the Earth, when we observe from the Earth, usually we can only observe the part of a lighted half of the moon from our perspective. If you see from this picture, start from a new moon, that is when the time the half of the moon that are bright. That and on the Earth, you can see half always the same half of the moon facing the sun is bright. However, when we're standing on the Earth, we cannot see any part of the light part of the moon. So therefore, when we look at the moon, we only see the dark half of the moon. And as the moon gradually rotates, we start to see gradually a little bit more of the lighted part of the moon. And so therefore, once before a half circle, so we call it a waxing crescent. Waxing means increasing. And after, like about a week away from the new moon, we actually have first quarter. Remember, the first quarter and the waxing crescent, the bright part is always on the right-hand side. As we keep moving towards the month, you are able to see more and more lighted half of the moon. So that is a waxing gibbous until almost like 2 weeks from the new moon, we're able to observe the full moon. As the moon keep rotating, instead we'll start to see less and less the lighted path of the moon. So we actually see the gibbous again, but this time it's what we call the waning gibbous. Waning gibbous, you can see the gibbous is actually on the left side, and then we go to the third quarter, which is basically the half of the disk of the moon. We lighted part of the moon we were able to see. Then the lighted part you can see is also on the left hand side. And finally, we go through the last week of the month, we see the waning crescent. The difference between waning crescent and the waxing crescent, the waning crescent is actually on the left hand side. So if you observe a moon in a crescent phase, that is how you tell if it's a waxing crescent or waning crescent. And then as the Earth, the moon orbiting around the Earth, and they finally again go to the new moon position and then restart the circle again. Now let's go ahead and take a time to look at the simulation. So you can see there's always the half of moon actually facing the sun is actually lighted because the moon actually reflects the sunlight. The moon itself does not emit its own light. Remember, we will start from a new moon position. Remember, when it is a new moon, the moon and the sun are basically on the same direction of the Earth. So therefore, the new moon you probably won't be able to see because you will see the moon and the sun will rise and set at the same time. However, after a while, you are able to observe the waxing crescent. You can see the moon is no longer in the same direction of the sun. So therefore, but the moon is not very far away from the sun. You can see that is the sun time. If you remember, during the day, you can still see the moon. That is the reason, because the moon is not exactly on the opposite direction of the sun. So during the day, you can still see the moon. you can see the crescent is getting larger and larger until we reach the first quarter about a week from the new moon. And then is waxing gibbous. During the waxing gibbous, you can see the rising and the setting of sun and the moon become further away in terms of time. And if we wait about a few days, then we will almost there, we will have what we call the full moon. So you can see during the full moon, the moon is exactly the opposite direction of the sun. So therefore, the full moon can only be observed during the night. So that means when the sun is rising, the moon already set. When the moon is rising, the sun is already set. So therefore, if you want to observe the full moon, it has to be during the night. And during the full moon, there's no way you can see the moon appear in the sky during the daytime. And if we resume the animation, and gradually you can see, you will see the waning gibbous. After a few days, the moon will become what we call the third quarter, right? And finally, the moon will become waning crescent and become thinner and thinner. And I have actually another simulation we can actually share, so we can put a moon in a different location. Now, let's actually go to maybe a location like a random location. Let's say this way. So this is the direction of the sun. So you can see the sunlight. How you can see there's always the half of moon that is actually light up by the sun. And how we determine what kind of phase it is, forget about anything mentioned here. We will draw a line. One line is giving you the dark side of the moon and the light side of the moon, or bright side of the moon. And the other line, we actually is Earth's moon bisectors. So that is the side of moon actually facing the Earth. So you can see the only part we can see the moon is actually the part in front of the Earth. So you can see among this part, we can see more than half of this bright side of the moon. So more than half. If you rotate a little bit darker on this side, but more than half, we actually have gibbous, because it's on the left-hand side is actually waning gibbous. And now we can also move the moon to another location. Like, how about here? You can see now the Earth able to see the half of the moon that's facing the Earth, but the half of moon facing the Earth, only small part is a bright part. A majority part is actually dark side. So we can rotate. We can actually move around to see what we actually see from Earth. We actually see is the crescent, because it's a crescent on your right-hand side. So this is actually what we call is the waxing crescent. I hope this simulation can help you kind of understand the phase of the moon better. Another phenomenon causing by the motion of the moon is actually the tides. If you live on the seaside for a while, you may know there's twice daily ocean tides. You can see the water first become higher, then gradually become lower and recede, and become higher again. And this is especially useful if you are going to sail a boat, because definitely you want to, for example, in this picture, you want to sail the boat on the high tide. because you can see when during the low tide, there's almost no water at all. There's no way you can start the boat. And also, if you want to set up your picnic chair on the seaside or beach side, so you'll want to make sure the water won't get underneath the chair when the tide start to get higher and higher. And there's also some animals that follow the high tide and the low tide. When it's a high tide, it helps some animals to go all the way to the seaside. When the water recedes from high tide and low tide, there are actually some like jellyfish, some like shells will be left on the seaside. So it's gonna be a good time to pick up those seashells, or it's a good time to look at what actually things are left behind the tides or the ocean. Now let's talk about why is the moon, not other objects, actually causing the tides. Remember, among all the celestial objects, the moon is actually the closest to the Earth. If you look at the relative location between the moon and the Earth, again, this is still not to the scale, but the size of the Earth compared to the distance between the moon and the Earth is not too small, so that if you still remember force of gravity we talked about, the force of gravity actually depends on the distance. So you can imagine on the side of the Earth that is actually closer to the moon will experience large force of gravity, a large attractive force. And the middle part of the Earth will experience a medium like force of gravity. However, on the opposite side, the side actually furthest away from the moon will experience the smallest force of gravity. So you can imagine if you put the front hardest and put the opposite side, the lightest, what will be result? You basically kind of pull the Earth towards the moon, especially the front side. However, the Earth's crust, the surface of Earth, like the rocks, they are solid. They can bear certain amount of force. They won't deform easily. So they can keep their shape. But there's also majority of Earth's surface is actually covered by the water. It's actually the ocean. And the water is actually liquid. So what happens? The liquids are much easier to change its shape, of easier to flow to respond to this larger force. As the result, you can see the front and the back experience differential force, the differences of the force. So therefore, as a result, the Earth's overall shapes of the Earth are being stretched. So therefore, it stretched harder on this side, that closer to the moon, and left behind the opposite side. Remember, the entire Earth is also kind of stretched a little bit, but left behind the opposite side. So it's like you are stretching hard on the front, but you are holding up the opposite side. As a result, the Earth, you can see the Earth's ocean around it develop what we call two bulges. The two bulge is exactly on the opposite side of the Earth. And remember, when the moon is pulling on the Earth is not at rest. The Earth is also rotate around its own axis. For example, if you are at a location in a high tide, and the Earth will rotate, keep rotating to a low tide point, and it will keep rotating. About 12 hours later, you will actually experience the second high tide. So typically, the timing between high tide and the low tide is a quarter of the day, is about 6 hours, and between high tides is half of the days, which is about 12 hours. Now let's take a look at the simulation, which will help you understand better of the tides. You can see here is the Earth, the blue is the ocean, and the small object here is a moon. You can see the bulge is always along the direction of the moon. But remember, the monthly cycle, the moon orbit around the Earth is about 1 month, but the Earth rotates around its own axis about like every 24 hours every day. So each location will experience 2 high tide and 2 low tide. But if you visit the seaside, you can see the high tide and the low tide is a little bit complicated, because if we include the effects of a sun, because the sun will also able to exert a force of gravity on the Earth. So it will actually change the tide a little bit. And the Earth's rotation will also increase the friction that the ocean actually being stretched or being pulled by the moon. So therefore, it's actually add another complexity to the tides. But the majority of the effects actually due to the moon's gravity on the Earth applied or stretched differently for the front side and the back side. And finally, let's talk about the eclipses of the sun and the moon. I would like to say the solar eclipse might be the most fantastic phenomenon we can observe, especially during the day when you have, like at noon, when you have suddenly you lost all the sunlight or most of the sunlight, and suddenly the outside become darker. It's most spectacular phenomenon. And because that when the day is suddenly become darker, and in the ancient time, people always associate solar eclipse with some bad things will happen. However, later on, we learned that those eclipses is actually caused by the different location of the sun, the moon, and the earth, and whether the sun is covered by the moon or whether the moon is under the shadow of the earth. So let's first to take a look at the solar eclipse. The solar eclipse is when the moon moves between the sun and the earth. So therefore, the moon's shadow and kind of cover part of the sun's surface when we observe from the earth. In reality, the moon is actually much smaller than the sun. By the way, this is not drawn in a scale, but this is just want to fit everything in the picture and you can still see everything. But in reality, the moon is much smaller than the sun. However, the moon is actually closer to the sun. So when we observe from the earth, the apparent size, so how large the moon appeared to us and how large the sun appeared to us is actually very similar, because compared to the moon's distance from the earth, the sun's distance is actually much further. So therefore, the disk of the moon and sometimes were able to cover the disk of the sun. Therefore, it covers most of the sunlight. Therefore, that is the moment we're able to observe what we call the total solar eclipse. The total solar eclipse happens when the entire surface of the sun, the disk of the sun, is covered by the moon. And this is illustration of total solar eclipse. The real picture of total solar eclipse is look like this. you can see the primary disk is covered by the shadow of the moon. However, the sun still have what you call this part is a corona of the sun. This actually is not very bright. When you can see the disk of the sun, you will not able to see the corona of the sun because it is actually cover large area, but is very dim compared to the disk of the sun. So that is how the total solar eclipse looks like, that the sky will suddenly become dark for a few minutes. But however, unfortunately, you can see only on the Earth, only on a certain location can observe the total solar eclipse, because only on the Earth, when the moon's shadow is actually casting on the Earth, that is a moment we can see the total solar eclipse. And you know the sun is moving, the moon is moving, the Earth is also moving at the same time. So the totality won't last for a very long time, typically only for a few minutes. And however, in a region that you cannot observe the total solar eclipse, the region sometimes you can observe what we call the partial solar eclipse. So that means you can still see a crescent of the sun. The moon only covered the part of the sun. If you remember, in 2017 solar eclipse, and in the metro Atlanta area, we actually are able to observe a very close to totality, but it's still partial solar eclipse. If you drive like 2 hours to the north, you're able to observe the totality. And there's also a third type of solar eclipse. We call it is annular eclipse. Annular eclipse is when the moon is not able to cover the entire disk of the sun. It's still left with a very thin ring about the sun. This is because the Earth and the moon's distance is also not constant. There's a certain time when the moon is actually a little bit further away from the Earth, or that is time when the sun is a little bit closer to the Earth. So therefore, the moon appears smaller or the sun appears bigger. So at that moment, the moon's surface not able to cover the 100% of the sun. So we have this annular eclipse. And in terms of lunar eclipse, a lunar eclipse is actually the Earth is on the way between the sun and the moon. So remember, we already talked about in the phase of the moon. The moon, we're able to see the moon because there's always a part of moon is actually to reflect the sunlight. However, if the Earth is on the way, if the Earth is cover the sun light from shining on the moon, or you can see the moon is entering the Earth's shadow. So we'll have what we call the lunar eclipse. The lunar eclipse won't be as significant as the solar eclipse in terms of our experience, because when you look at the lunar eclipse, it always happens during the night in what we call the full moon position, because the moon has to be on the opposite side of the sun compared to the Earth. And usually the moon is not very, very bright during the night. The night is always probably dark. So therefore, the lunar eclipse won't give you dramatic change of the light during the night. Let's see how the lunar eclipse looks like. There are also partial lunar eclipse and the total lunar eclipse. And you can see that the partial one is similar as the phase of the moon, but remember that won't last for very long. And you can see that partially the moon's lighted part or bright part is under the shadow of the Earth. And this is actually in the middle is a picture of the totality, the total lunar eclipse. That is, the moon is 100% on the shadow of the Earth. But you may be curious about this moon does not look like it's 100% dark. What happens? Because we are all assuming that the Earth actually blocks the sun that go all the way directly from the sun to light up the half of the moon. But there is actually some sunlight actually refracted by the Earth's atmosphere, mostly the red light. You can still kind of reach the moon when the moon is 100% on the Earth's shadow. So this actually gives the total lunar eclipse the reddish color. And sometimes people like to call this bloody moon. So unlike solar eclipse, only a small region on the Earth, and for a very brief amount of time, you can observe it. So for lunar eclipse, as long as you are on the night of the Earth, you're able to see the moon, not just a very small region. As long as you are on the night side of Earth, you're able to see the moon, you will observe the lunar eclipse. So therefore, to most of people, lunar eclipse is easier and more often to observe than the solar eclipse. Because both the solar eclipse and the lunar eclipse happen at a certain configuration of the sun, the moon, and the Earth. Remember, this is always a cycle. So Earth is already orbiting around the sun and the moon always orbiting around the Earth. So there is no like once it happened, it won't happen again. So it actually follows some kind of regularity in order for us to see the solar eclipse and the lunar eclipse. Therefore, by looking at the motion of the Earth around the Sun as well as moon's motion around the Earth, we can actually do a calculation to predict the future solar eclipse and the lunar eclipse. If you take a look at this calendar, it's basically give you like, this is basically solar eclipse. The darker one is a lunar eclipse. You can see it basically gives you a prediction of what time we're able to observe the solar eclipse and the lunar eclipse. The closest one is about to happen around like 2024. And you can see for the solar eclipse, it will also give you information of the visibility. And for lunar eclipse, you can see basically there is, as long as you're in the night side, you are able to see it. You can see from this table that lunar eclipse and the solar eclipse actually happens pretty often. It just really depends on which location on the Earth you will need to, or you are able to see them. That is all I want to talk about in Chapter 4. In Chapter 4, we first talk about the coordinate system in celestial sphere, and then we talk about the cause of season is due to the 23.5 degree tilt of Earth's rotational axis. And then we mentioned about the phase of the moon, how we actually able to observe different phases of the moon. And in addition, the moon also exerting the differential gravitational force, which actually causes the high tide and the low tide on the Earth. And then finally, we talked about how the solar and the lunar eclipse actually appear and how we're able to observe them.